Hello, math nerds. Students been struggling a lot lately with trigonometry, and I want to make sure that that's not going to be a problem going forward. So I thought maybe put together a video where I just cover as many of the basic concepts as possible, just trying to clear up any confusion about what exactly is going on. Because I don't know exactly where the struggles are coming from, I'm going to be forced to review a ton of things. Some of them could be considered extremely basic for some, but others might not think so. So we're just going to take it step by step and show every possible little thing that I could think of that may or may not be causing an issue. Let's begin with the very most fundamental thing that I could think of, and that is our terminology of sides of angles. Angles, classically, and I'm not quite sure why, were decided that they open counterclockwise and that they always begin at the positive x-axis. We would call that the initial side. Now, when an angle is in standard position, the initial side is always the positive x-axis, always. The terminal side is the side of the angle that we can see when we're doing trigonometry. For example, I could draw it over here in quadrant 2, and we would call this the terminal side. Terminal means ending. We're literally saying that this angle started here and ended here. But like I said before, angles are supposed to open counterclockwise. So as long as they do open counterclockwise, we could say that this is a positive angle. Now, it doesn't have to open counterclockwise. It could open clockwise. And if it opened clockwise, it would begin at the positive x-axis because that's where all angles begin, and it would end there. And this would be considered a negative angle. There. And we typically use the Greek letter theta to represent our angles. So just get used to seeing that, T-H-E-T-A, theta. And while we have this picture, we might as well review the concept of what it means for two angles to be coterminal. This terminology means two angles that both begin here, both end in the same spot, so for example, here, but have completely different measures. For now, let's talk about degrees. If I draw an angle in quadrant, 3. Let's just draw one in quadrant 3. Remember, all angles begin at the positive x-axis. I'm going to throw this one in quadrant 3. Picture not drawn to scale because it never is. And I say, okay, if this is 0 degrees, this is 90 degrees, straight line, 180 degrees, 270 degrees. Let's just say that this is, 30 degrees because that's one of our special angles, past 180 degrees. So let's just say the way this sits, this angle is a 210 degree angle. There are an infinite number of positive angles that land here, an infinite number of negative angles that land here, and we need to be comfortable with finding those angles. So here is the original positive angle. Original positive angle, 210 degrees. If I said, give me another positive angle that is coterminal to 210 degrees, it would be the same as starting here, going here, and then turning another full circle, whee, like that. What does that look like, though? That looks like start here, go to our terminal side, but don't stop there. Go another full circle because we're crazy. Why not? And do that. Yes, it began at 0. But notice from here to here was the same as the green angle. I went a total of 210 degrees. And then, because we're nuts, we decided to go another full circle, which gives us this positive angle is the original 210 degrees and another 360 degrees, which is 570 degrees. So the positive angle 570 degrees is coterminal to the positive angle 210 degrees. Of course, I didn't have to have positive only. I could have said, well, give me a coterminal angle, meaning begin here, end here, that's negative. Then that is the shorter trip. Let's use red, it'll show up better. Beginning here and then going clockwise to there. This is really short. It's really not that far of a distance, but mathematically, the easiest way to calculate it is to pretend you took the red trip of 210 degrees and then said, you know what, I'm going to turn a full circle. Not the purple circle. No, I'm going to go, that strangely rhymed, I'm going to go the other direction to complete the red circle. Mathematically, that negative angle would have been saying, I could have gone the 210 degrees, but then turn a negative 360 degrees. The net result is this tiny red line. I'm aware this tiny red line did not start at positive 210 degrees. I know that, but its value can be computed by saying, go the green trip, then turn a whole negative circle, and that's going to give me a negative, I don't know, I can't do basic maths. What is it, 150 degrees. There you go. So if you began here and then went clockwise 150 degrees, you'd land right there. So 570 degrees is coterminal 210 degrees, which is also coterminal to negative 150 degrees. I could keep subtracting 360. I could keep adding 360, and I would keep landing here every single time. All right. So that is the first quote-unquote basic concept. The next, let's just say concept, that way I don't have to keep saying basic because I don't want anybody to be offended by this, is we all need to be clear with the fact that degrees are a man-made thing. There is no such thing as degrees. So to say that there are 360 degrees in a circle is, well, it's baloney. Okay, it is. It's just baloney. It's not a truth of the circle. It's a convenience. We choose 360 degrees to say there's 360 degrees in a circle simply because we can divide it by a lot of stuff. It's a convenient number. But a truth of a circle is that every circle has exactly 2 pi radians within it. A radian being a type of angle that is the exact same measure as the length of the arc it creates. I know that's a weird thing to say, but it literally means take the radius of a circle and whatever that radius is, create a curved line with the exact same length, close up the angle, and that angle would be called a radian. There are exactly 2 pi radians in every circle. So a little bit more than 6 1/4. It's actually a little bit more than 6.28, but we say there are 2 pi radians in every circle because it's a truth of the circle. Made up truth. Okay, if there are 360 degrees in every 2 pi radians, or if there are 2 pi radians for every 360 degrees, whichever one you're more comfortable with saying, we all need to be comfortable with the fact that I can divide both these numbers by 2 and say that there are 180 degrees for every pi radians, or again, you could say there's pi radians for every 180 degrees, whichever one you're more comfortable with. But radians are the actual true unit that we're going to be measuring things in. So if this is 0, but it's also 2 pi, it's also 4 pi because these are coterminal for turning whole circles. Halfway through the 2 pi gets me to right here at pi radians. Now halfway between 0 and 1 is 1/2. So halfway between 0 radians and pi radians is going to be 1/2 pi radians. But we typically don't write the 1 in front of the pi. We just write pi over 2. But that is 1/2 pi radians. Halfway between 1 and 2 is 1 1/2. But mixed numbers, really not the preferred numbers that we want to work with Trig. So what we're going to do is, instead of saying 1 1/2 pi's, because that's weird, what we're going to say is 3 pi over 2, literally 3/2 of a pi, 3 pi over 2 radians. And all these things are in radians. We don't have to write rad. Radians is the assumed unit of measure. Now, these 4 are called your quadrantal angles, but they're not the only ways that we subdivide our circles. But before we go into the other types of subdivisions that are useful for us, we do need to review the concepts of our special right triangles that hopefully were learned in geometry. So pictures not drawn to scale because they never ever are, but there are 2 types of special right triangle that we want to focus on, and those are the isosceles right triangle, better known as the 45-45-90 triangle, actually. And the 30-60-90 triangle. Like I said, pictures not drawn to scale. Now, I don't want anybody to think that all 30-60-90 triangles are oriented this way, so I will draw this one again, but with the 60-degree angle being in the bottom left, because what I'm doing is I'm treating this bottom left-hand position as standard position, which is down here at the origin. So just rotating this triangle. Oh, that line's crooked. Make it taller that way. Like I said, picture not drawn to scale. But if I put the 60-degree angle down here, that puts the 30-degree angle up here. All right. Now here's the thing. I haven't decided the size of any of these triangles, so I can assign any value I want to the leg of this right triangle. All that matters is that they're the same number. Out of convenience, we typically say that that side length is a 1. But realize it could be a 2, and a 2, a 7, and a 7, I don't know, a 24 and a 24, whatever. It doesn't matter. The point is they're the same. We use nice small numbers out of convenience. Now, if we do the Pythagorean theorem, the hypotenuse of this right triangle has a value of the square root of 2. So I mentioned a moment ago subdivisions of our 2 pi's. 45 degrees is a very good subdivision. However, radians, like I said, the preferred method. So instead of saying 45 degrees, what we say is its radian measure of pi over 4. 45 degrees is half of 90. And since 90 degrees is represented by pi over 2 radians, half of pi over 2 radians gets us this pi over 4 radians. However, whenever I draw my special right triangles, I'm always going to use 45 and 90 for the isosceles, because the pi over 4, pi over 4, pi over 2 triangle just doesn't roll off the tongue as nicely as the 45, 45, 90. Now over here, we have 30 and 60. As it turns out, 30 degrees and 60 degrees are also very nice subdivisions of 360 degrees. But again, radians, preferred values. Doing this kind of out of order, but 30 degrees is 1/6 of 180 degrees. So we could say it is 1/6 of pi radians, which we represent as pi over 6. 60 degrees is 1/3 of 180 degrees. So we represent that as pi over 3 radians, like that. So anytime you see a pi over 4 of any kind, that's 45-degree angle somewhere. Anytime you see a pi over 6 of some kind, that is a 30-degree angle somewhere. And anytime you see a pi over 3, that is a 60-degree angle somewhere. Like I said, I got a little ahead of myself. Let's fill out the side links on this 30, 60, 90. Like I said, we pick nice small numbers because they're easy to work with. And in a 30, 60, 90 triangle, we don't have any two sides that are the same length. In fact, because we have 3 different angles, we have 3 different length sides. The side across from the smallest angle, 30 degrees, will always be the shortest leg. So the side across from the 30 will be the shortest. Assign it any value you want, but 1 is very convenient. And in this triangle, across from the 30, 1. In a 30, 60, 90 triangle, the hypotenuse is always exactly double whatever the shortest leg was. So in this triangle, we put a 2 on the hypotenuse. But remember, I said this number could be anything you wanted it to be. So if this was a 7, this would be a 14. It's just literally double whatever the shortest leg is. And if we follow the Pythagorean theorem, the side across from the 60-degree angle will always be a square root 3 of some sort. And you'll see what I mean by the of some sort in just a moment. All right. So it is time to take our quadrantals, our quadrants 1, 2, 3, 4, and start subdividing them. That way we can see where all of these things would land, because knowing those and knowing these are the key to mastering trigonometry. None of these pictures will be drawn to scale. I apologize, but it's just really not worth the effort. It'll make the videos too long. So I say this is 0 radians and this is pi radians. Halfway between 0 and pi is 1/2 pi, or pi over 2. Halfway between 1 and 2 pi's is 1.5 pi's, better known as 3 pi over 2. Already stated that before. Time to subdivide into fourths. We'll start with fourths. So what I'm going to do is I'm going to use a green line to represent the terminal side of my angles. Just like I did before when I was using that green highlighter, I had the initial side on the positive x-axis because that's always initial. And I drew another green line somewhere else. I think I drew them over here in quadrant 2 to represent the terminal side. I'm going to be drawing terminal sides at every 45 degrees, which means every 1/4 of this pi. Now I know pies are normally, quote unquote, the pies that you eat, they're normally round, but we're just going to have to think about math pi here. Our job is to take this straight line, realize it represents an angle, a straight angle of 180 degrees, and we need to subdivide this 180 degrees into 4 equal parts. Well, good news. Pi over 2 already divides it into 2 equal parts. So all we have to do to get 4 equal parts is to cut our halves in half. So literally, halfway between 0 and 90, halfway between 90 and 180, halfway between 180 and 270, halfway between 270 and 360. This is where you would find your first pi over 4 radians, starting here, going here. Now pi over 2 is the second pi over 4. It's just reduced. Then opening all the way to this line would give me my third pi over 4. 1 pi is 4 pi's divided by 4. That is 4 fourths. Here is 5 fourths of a pi. This is 6 fourths of a pi. This line would represent an angle that opened all the way to 7 pi over 4. And you guessed it, 2 pi is also 8 pi over 4. Now I could continue going around, 9 pi over 4, 10 pi over 4, 11 pi over 4, 12 pi over 4, so on and so forth. But that's a little bit of an advanced topic that we'll get to here in a little bit. What I wanted to point out with these subdivisions that I've drawn is that I can create right triangles by dropping lines straight down. We can now take these right triangles, well, I guess these right triangles, and fill them out with the side lengths of 1, 1, and root 2. They're all going to be a 45-degree reference angle, though, at the x-axis. There. In quadrant 1, both x and y are positive numbers. So this x value is 1, this y value is 1, and that would make this hypotenuse a square root 2. Now, when we move over to quadrant 2, we have to be careful. This vertical line is still positive here, but our horizontal side, which is always the x-axis, it's actually on the left side of the coordinate system. That means that this x value is a negative x value, so we'll call it negative 1. The hypotenuse, which is technically the radius of a circle, is always going to be a positive number. So the green lines will always be positive because they represent the radius of a circle. I just didn't draw that circle. However, every point on the edge of this circle is the square root of 2 away from the center of my graph. Down here in quadrant 3, I still have this negative 1 as my x value, but my y values are negative as well. So now I have a negative 1 triangle. Radius remains root 2. And then over here, y is negative, but we already have the positive x drawn on there, and that's going to give me a root 2, like that. So anytime you're asked to find trig of something pi over 4, so any number of pi over 4s, you're going to be using one of these 4 triangles, which one is going to be determined by how many pi over 4s do I need to go. So, for example, where is, I don't know, 3, how about 23 pi over 4? You could go through the really hard task of counting them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. This is quality content here. This is 23 pi over 4. Or we could have said that 23 pi over 4 is almost 24 pi over 4, which is 6 pi. So this being all of the even pi's, 0 pi, 2 pi, 4 pi, 6 pi, I would need to be 1/4 of a pi, or 1 pi over 4, before this. Boop, right here. And I would draw just this quadrant with this triangle in it, knowing x is positive, y is negative, and root 2 is the radius or hypotenuse. I could then do any of these 6 trig functions there. Okay? Okay. Now, let's subdivide according to the 30-degree angle and the 60-degree angle. Now, the 30-degree angle is more of a pain in the butt. So, I'll save that one for last. Let me save that one for last. Let's go with the 60-degree angles first. Well, secondly, but before the 30s. And the reason why 60 is easier is because it's exactly 1/3 of this pi. So let me draw these in, I don't know, purple? Let me draw them in purple. My job is to take this straight angle and divide it into 3 equal parts. Picture not drawn to scale. I am going to do my best here. Let's see. I'm going to have a 60-degree angle like that, and then another 68 degrees like this. That's pretty close. That's pretty close. Then I'll have 60 down here past pi and 60 over here before 2 pi. Throw my pi over 2, my 3 pi over 2 back on there. And while I'm at it, shoot, let me throw a 2 pi back on there. All right, let's count thirds. This is 1 pi over 3 after 0. This is 2 pi over 3 after 0. This number is 3 pi over 3, 1. Here is the 4th pi over 3. Here's the 5th pi over 3. And then 2 pi is actually the 6th pi over 3. Once again, drawing my vertical lines creates 4 triangles. 4 right triangles. And I said these are the 60s. What's a good color? Green will work for my angles. This is a 60-degree reference angle, and so are the other 3. Now, obviously that means the leftover angles are 30s, but I'm not going to write those in because all I care about is the size of the reference angle. And now I can fill this thing out with the same numbers that I put on this triangle, with the root 3 in the vertical y position, with a 1 in the horizontal x position, 2 in the hypotenuse, better known as the radius position. So we said across from a 60 is always going to be a root 3. Across from the 30 is always going to be a positive 1. Well, no, excuse me, a 1, not always a positive, but always a 1. In quadrant 1, both x and y are positive, with a radius of 2. Now, they're all going to have a radius of 2 because, remember, this is a circle that I'm just not drawing all of. And this point is on the terminal side of an angle, but it's also on the outside of a circle. Now, over here in quadrant 2, just like I said before, my y's remain positive, but my x's have become negative. In quadrant 3, both x and y are negative. And in quadrant 4, x remains positive, but y is negative. These are the 4 60-degree reference angles. Remember, it's 1/3 of a pi. So that means I can perform any trig at any number of these pi over 3s. Any trig at any number of these pi over 3s. For example, what's a number that would be good? How about, hey, you know what? How about 23 pi over 3? Again, we could count. Ready for this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Out of complete coincidence, I landed down here in quadrant 4 again. But this is the 23rd pi over 3 right here. How would we have recognized that? Because 23 over 3 is almost 24 over 3, which is 8 pi. And once again, this is where we find our even pi's. So 0, 2, 4, 6, 8 pi's all land here. So this is 1/3 of a pi before right here. So that goes here. So if I wanted to know what is tangent of 23 pi over 3, I would say it is y over x right here. This is the triangle I would draw, and I would get -√3 over 1. So anytime you see any number of pi's over 3, you're going to draw one of these 4 60-degree reference angles. And now for the 30-degree reference angles. The only reason why these are a pain is because 30 is a divisor of 60. And that's really the only reason why they're more difficult, quote unquote, to work with. It's not even that they're harder to work with, it's that it's more difficult for me to draw them all. So I have to make my picture a little bit larger. I think that's larger. Do my best here. See, I've drawn green, I've drawn purple, I haven't drawn blue. I'll make my 60-degree reference triangles, or all of my 30-degree reference angles. There we go. Those will be the blue ones. So if I'm talking about pi over 6s, sixths of a pi, I have to literally cut this half of a circle, this pi, into 6 pieces. And luckily it's already cut into 2 pieces. So if I can get 3 here and 3 here, I have all 6. And that's what we're going to do. I'm going to take each of my quadrants and divide them into 3 equal parts to the best of my ability. I hope that's large enough for me to be able to write in there. Let's see, make them bigger. To focus on the ones that I'm going to draw in. Wow. Go home, 30-degree angles. You're drunk. Am I right? Yes, of course I'm right. I'm always right. Just don't ask my wife. Okay, so talking about the pi over 6s. Okay. Here's the first pi over 6. Now here's the second pi over 6. But you know what 2 pi over 6 equals? It equals pi over 3. You see, we already have the pi over 3s. So yes, this is 2 pi over 6. This one, this is the third pi over 6. Here's the fourth pi over 6, but guess what that is? That's 2 pi over 3, which again, we already have. It's right there. This would, wow, this one is going to be really tough for me to write in. I am so sorry. But this one is my 5th pi over 6. This one is 6 pi over 6, which of course is 1. Here's my 7th pi over 6 away from 0. This is 8 pi over 6, but that one does reduce to one of the ones that I had in the purple ones, 4 pi over 3. Here's 9 pi over 6. Here's 10 pi over 6, which does reduce to, again, one of the purple ones, 5 pi over 3. 11 pi over 6. And then lastly, 2 pi is 12 pi over 6s. Okay. Oh boy, picture really not drawn to scale. However, here, especially these ones on the left, yikes, are the 4 30-degree reference angles. Wow, this one's going to be tough. So I'm going to put my little 30 degrees in all of the standard positions. There we go. The reason why I haven't drawn these is because those are 60-degree reference angles. So there's 4 45-degree reference angles, 4 60-degree reference angles, 4 30-degree reference angles. We don't count those as 30-degree reference angles because they're 60-degree angles. Before, I said that the side length across from a root of, of a 30 degree should always be labeled as a 1 for easy mathematics. So here in quadrant 1, this side length is a 1. So the y value here is a 1. The x value is across from that angle. That angle will be 60, so this is a root 3. And the radius, hypotenuse, is a 2. Okay, well, all 4 of these are going to have the same radius. Remember, it's a circle. I'm just not drawing all of it. Over here, my y value, the number across from the 30, is still just positive 1 because in the second quadrant, y values are still positive. But this x value, since I'm on the left side of the quadrant system, is negative root 3. And then down here in quadrant 3, both x and y are negative, so this will be a negative 1. Very last one, over here in quadrant 4, x is positive, but y is negative. All right. What this means is we can do trig of any number of pi over 6s. And we'll be drawing one of these 4 blue triangles for pi over 6s and filling them out with the appropriate side lengths. For example, and I don't want to land in quadrant 4 again, so let's pick a different number. How about 17 pi over 6? I don't know, I'm just making this up. We could count. Here we go, counting to 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There is 17 pi over 3. Or we could, 17 pi over 6, excuse me. Or we could realize that 17 pi over 6 is almost 18 pi over 6, which is 3 pi. Remember, if my even pi's are over here, my odd pi's, 1 pi, 3 pi, 5 pi's, are all happening on the left side. So this is a 30-degree angle before 3 pi, and I would draw that triangle. So if I wanted to do cosine here at 17 pi over 6, I would have drawn only quadrant 2 with only this 30-degree reference triangle in it. And cosine would have been x over r, or negative root 3 over 2. And that is how we use our reference angles and our special right triangles and our fractions of pi's to evaluate trigonometry. Now, I did mention x, y, and r a few times when I was drawing out my reference triangles and things like that, but I do think it's important to really list out which ones use what. Now, if I were to draw a triangle in quadrant 1 only, and realize this works everywhere, and I don't know, I'll make this triangle purple, how about that? Picture never drawn to scale, because why would it be, right? Okay. Call it a right triangle. That way we can actually do some trigonometry. And let's throw some values on there, or even better yet, just some letters. If my theta is in standard position, meaning begins at the positive x-axis and then ends somewhere not the positive x-axis, I guess, anywhere we want it to be, I could use tried and true SOHCAHTOA that is taught to us in geometry. And then you would just need to know what the reciprocal of sine is. Know that it's cosecant, flip it over. Know that the reciprocal of cosine is secant, flip it over. Know that the reciprocal of tangent is cotangent, flip it over. And that will almost never fail. You say almost never. See, the problem with SOHCAHTOA is that you're assuming that you're always going to have a triangle. But you don't always have a triangle. Specifically, if you're ever on the x-axis or on the y-axis. So if you're asked to evaluate trigonometry that lands on one of your quadrantals, you're not going to be able to draw a triangle. You're not going to be able to use SOHCAHTOA. And I'm a fan of having one method that always works for all trig. That means we have to let go of this acronym and instead have to use X for horizontal, Y for vertical, and R, radius, hypotenuse. So let's get really clear about this. The X value in these triangles, and by these triangles I mean the reference triangles that we draw, is always the adjacent side. Whereas the Y value is always the opposite side. The radius is always the hypotenuse. That's true for everything. Unless, of course, like I said, you're on one of the 4 quadrantals. So instead of saying that sine is opposite over hypotenuse, what we're going to say is that sine of theta is y over r. Its reciprocal then, cosecant of theta, is r over y. Cosine of theta is x over r, not adjacent over hypotenuse, x over r. Its reciprocal then, secant of theta, is r over x. And then tangent of theta is not opposite over adjacent, y over x, making its reciprocal cotangent x over y. Now, as you saw in the 3 different sets of subdivided 2 pi's, when I was drawing my reference triangles for 45 degrees, 60 degrees, and 30 degrees, x and y are not always positive. Sometimes they're positive, sometimes they're negative. Now, the radius is always positive. But because sine and cosecant are using the letters y and r, their symbols, SIGN, meaning positive or negative, are always determined by the y value, because r is always positive. So if y is positive, sine, and because of it, cosecant, is positive. So where is sine positive? Where is y positive? Quadrants 1 and 2. Now cosine uses the letters x and r, which, so does secant. Remember, r is always positive. So the symbol in front of cosine, and also because of that secant, that symbol is determined by the x value. If x is positive, cosine and its reciprocal are positive. If x is negative, cosine and its reciprocal are negative. So where is x positive, meaning where is cosine positive? Quadrant 1 and quadrant 4. Tangent and its reciprocal use the y and the x values. They do not involve the radius. So anytime you do a positive number divided by a positive number, you get a positive result, like quadrant 1. But you also get a positive result if you do negative divided by negative, which is what happens in quadrant 3, where x and y are both negative. That means tangent and its reciprocal are only positive when x and y have the same symbol. Tangent and its reciprocal are negative when x and y do not have the same symbol. And the trick we use for that is A for all, S for sine, T for tangent, C for cosine. And these tell you where these, and then their reciprocals, are positive. All three, sine, tangent, cosine, and their reciprocals. All students take calculus, I hope. With all of that knowledge, we have the ability to just start doing some trig questions. I don't know. Let's throw one out there. How about finding cosecant of, I don't know, maybe a 15, 17, 18, let's do 19. How about a 19 pi out of 4? That feels good. So what are we supposed to do? Well, first we decide where this angle is going to land. The easiest thing to do, I think, for me at least, is to build a mixed number out of this. It's one of the few times where a mixed number is actually going to be useful to us. That and baking cookies, I guess. But if you divide 19 by 4, it's going to go in 4 times. So it's going to go 4 full pies, but there will still be, because 4 times 4 is 16, a remainder of 3. So this angle of 19 pi over 4 is 3 pi over 4 after 4 pi. Well, 4 pi is an even pi. 4 pi then is the positive x-axis. This is 3/4 of the way to the next pi. So almost to the 5th pi. That's going to put this thing squarely in quadrant 3. Because this would have been pi, it's also 3 pi, and then it's also 5 pi. Maybe this is easier for you to realize that it's almost 20 pi over 4, which is 5 pi. It's almost 5 pi. I don't know. It doesn't matter which way you choose. So now I'm going to draw a reference triangle, picture not drawn to scale. Now we ask ourselves, what kind of reference triangle? So first we decide where it is. Then we ask ourselves, what kind? It is a 1/4 kind. And a pi over 4, remember, is 45 degrees. So this is a 45-degree reference angle. 45-degree triangles are isosceles. Well, 45, 45, 90-degree triangles are isosceles. So we would be throwing on there a 1, 1, root 2. However, look where we are. We're in quadrant 2. In quadrant 2, our y values are positive, but our x values are negative. Our radii are always positive. Now we ask ourselves, which fraction am I building based on cosecant? Well, cosecant says r divided by y. So I come over here and I say the cosecant of 19 pi over 4 is this r over this y. And there you have it. How about a different one? How about, I don't know, tangent of, let's do a pi over 3. You know what? Let's do 19. 19/3 this time. Again, I'm just a fan of using the mixed numbers. And I would say 19 divided by 3 is 6. 6 times 3 is 18. So there's going to be a remainder of 1. 1 more pi over 3. This is literally a pi over 3 after 6 pi. And 6 pi is the positive x-axis. This is quadrant 1. So first we decide where we're going to draw a triangle. Then we decide what kind of triangle. You see, this time it was a pi over 4 triangle, which is 45 degrees. This is a, pi over 3 triangle, 180 over 3, which is 60. So I have a 60-degree reference angle in quadrant 1. You know, the nice thing about quadrant 1 is that everything is positive here. But now we fill out a 30, 60, 90 triangle, where the 60-degree angle is always across from a side of length root 3. Like I said, everything's positive here. That makes this the 1 because it's across from the 30, and this the 2. At this point, now that we know where we are, what kind of triangle we're dealing with, we build our fraction. Tangent is the y value over the x value. Y over x, root 3 over 1, or just root 3. And just to say it's complete, let's go ahead and do an over 6. How about secant? No. Let me do cosine. Cosine, it's reciprocal. Let me do cosine of 19 pi over 6. Let's figure out where that is. Well, 19 divided by 6 is 3. But just like before, 3 times 6 is 18 with a remainder of 1. Be careful though. This is a pi over 3 after 3 pi. Oh, 3 pi is the negative x-axis. So I'm after the negative x-axis. That puts me in quadrant 4. So I know I'm drawing a triangle in quadrant 4. Then I ask myself, what kind of triangle? It's an over 6. 180 divided by 6 is 30. So this is a 30-degree reference angle. Now I can fill out my 30, 60, 90 triangle. There's always a value of 1 across from a 30-degree angle, but in quadrant 3, both x and y are negative. So this is a negative 1. That makes this root 3 negative root 3. And the hypotenuse, the radius, is a 2. And cosine uses the x value over the radius. Negative root 3 over 2. Whew, that is a long video, but you have seen how to evaluate standard trigonometry using special right triangles. I hope that helps.